Welcome back, everybody. Today we're going to look at our 8th topic in our AP review series, and we're going to move on from derivatives now. We're going to move into the integral, and I want to actually begin with the graph interpretation of what the integral represents, and then how to make approximations of the integral using various strategies. So the next chunk of our review lessons will center around the integral from a to b of some function f of x dx. Remember that we call f of x the integrand. A and b are the limits of integration. We are integrating from a to b. And then dx, that's our variable of integration. We're integrating in terms of x. So if we look at a basic graph here. Okay, let's say that this is f of x. And this is a, and this is b. When we look at the integral from a to b, this is going to represent the net area between the curve and the x-axis. That word net is important because net means we're going to take area that's above the x-axis, and we're going to call that positive area. And then the area below the x-axis will be thought of as negative area. So it's going to take the area of this region minus the area of this region to create a net area. So whenever we see this integral, I always want you guys to think of this as area under the curve. Area above is positive, area below is negative. When you combine the positive and the negative, you get a net area. If we were asked for a total area, we would want to make all of it positive by doing an absolute value look at this graph and making this red region positive. And you could do that by splitting it, subtracting, or several different ways depending on how the graph sets up. But this is more just a general overview of what that integral there represents, net area under the curve. So we talked about in class this year a lot of different ways to do this. We're going to look at anti-differentiation, the fundamental theorem of calculus in the next episode. We looked at finding the area using geometry and problems where that's set up. But today I want to focus our second half on how do we approximate it? So approximations of the definite integral. And we have 4 that I want to make sure that you are comfortable with. First is the left-hand Riemann sum, or left-hand sum. Second is the right-hand Riemann sum. Third is the midpoint sum. And then the fourth is the trapezoidal sum. These are the 4 that you want to get very comfortable with. Now, a couple key points to remember. Remember, the trapezoidal sum is the average of the left and right-hand sums. That's a nice little fallback if you forget how to do trapezoidal. So just be, I'd be ready for all 4, but it's just a nice little backup plan if that were the case. Now, graphically, what these would represent, so if I draw a function that is increasing like this, and a left-hand sum means the left corner, top left corner of each rectangle is on the curve. So for an increasing function, remember that a left-hand sum under approximates. This is the left-hand sum. If I do a right-hand sum on an increasing function, I put the right corner of each of my rectangles on the curve, we can see that that creates an overestimate of the true area under the curve. If I were to flip and make these decreasing, it would be the opposite. So understanding what these look like visually helps you if you forget the rules about under and over approximation. Remember, specifically, I'm going to key on the trapezoidal sum. If a function is concave up, remember that trapezoids overestimate. And if a function is concave down, remember that the trapezoids underestimate the true area. The midpoint is the flip of the trapezoidal, because the other direction. So I don't know if I'd focus so much on memorizing those rules, but I would focus on being able to create the picture. And then from that picture, look at, does the left hand under or over, does the right hand under or over, does the trapezoidal approximate? And I'm going to focus this video very much P style, so we're going to look at a table. So a lot of these problems on your AP exam give you a chart. Usually it's not generic, like x comma f of x. Usually it's some application, something similar like that. But let's say you have a table, and I'm going to give you x values of 2, 4, 5, 8, and then 10. And then the y values, let's say they're 1, 2, 4, 5, and then 7. And our goal is to approximate the integral from 2 to 10 of f of x using, let's start with the left-hand sum. So when I look at this table, I can visualize my rectangles here. The base of each rectangle is the jump in the x values. There's going to be 4 rectangles to define this table. Usually they'll say something in the problem to tell you how many rectangles to use for it. And I like to go ahead and mark the jump. So 2, 1, 3, and 2. That's going to be the base of each of my 4 rectangles. The heights will come from the y values. And which y values you use depends on which approximation. So for a left-hand sum, I'm going to start with the leftmost y coordinate, my first height, and I'm going to use the first 4 heights. I will not use the rightmost height. So we're going to have our first rectangle will be 2 times 1 plus, next one is 1 by 2. Next one is 3 by 4. And then the last one is 2 by 5. We add all of that up, 2, 4, 16, 26. And we can see that that's an underestimate because this is increasing. We left off the biggest value. All right, part B, right-hand sum. Same idea this time. Our bases are the same. The difference is I'm going to use all of the heights. My 4 heights will be the rightmost heights. I will not use the 1. So my first rectangle, and I'll just go to the right, is 2 by 2 plus 1 by 4 plus 3 by 5. And then the last one is 2 by 7. So total we get 4, 8, 23, 37. And that's a nice little overestimate because we left off the smallest y value. Okay, part C. We're going to look at the midpoint sum next. Now, when I do my midpoint sum, I'm going to use only 2 rectangles this time because in order to do a midpoint sum, you have to cut down the number of rectangles because your midpoints will be going, they're going to be further. You need a value in the middle to serve as the height. So my first rectangle will go from 2 to 5. So it has a base of 3. And I'm going to use the height that's right in the center, right in the middle of that rectangle. My second rectangle is going to go from 5 to 10. So it's got a base of 5. And the height I will use is the 5. So we get 3 times 2 plus 5 times 5, which will be equal to 6 plus 25 is 31. Okay, that's my 3 rectangular approximations. Now I want to look at the trapezoid. And just for ease of access here, I'm going to recopy this table on the next page. So x, f of x, 2, 4, 5, 8, 10, 1, 2, 4, 5, 7. And let's work through the trapezoidal sum. And like I said before, this is going to be the average of the left and rights, but most of the time you're not doing all of them in one problem, so it's good to know how to do the trapezoid itself. So just like before, I can visualize my trapezoids. Remember, they're on their sides. The height of each trapezoid is the jump, so 2, 1, 3, and 2. And then the bases of each trapezoid are the two y coordinates that the trapezoid spans. So our formula is half the height, so half the jump times the sum of the two y values. That's the first one. Plus half the jump times 2 plus 4. Plus half the jump times 4 plus 5. Plus half the jump, 5 plus 7. So I put together these four, and that's going to be my trapezoidal sum. So this first one is 1 times 3. So that's 3. The second one is 1/2 times 6. So that's another 3. The next one is 3/2 times 9. So that's 27 halves. Plus 1 times 12. That's just going to be 12. So if I can put all of this together, this is 6, that's 18. So that's 36 over 2 plus 27 over 2, which will give me a total of 63 over 2, which is what, 31.5. And if I go back to my previous problem, I can see that the average between these two should be, if I did everything correctly, it's 31.5. So it's good to go. So there's our trapezoidal sum. All right, so in summary, guys, I'd be ready to not only understand the integral, but be able to approximate it using these four methods and know whether or not they'll give you an under or over estimate. Remember, trapezoidal and midpoint are based on concavity, and then the left and right hand sum are based on increasing and decreasing. And usually that's given in the problem or spoken in the problem in some way. All right, guys, I look forward to seeing you next time. Keep up with the studying. We're going to look at the fundamental theorem of calculus in the next episode. Have an awesome day.